Hello everyone, my name is Alan from the Hong Kong Polytechnic University. Today we would like to talk about DSP for short reach optical communications to try to give an overview of what has happened and discuss what we think will happen in the future. This is a joint work between me and our colleagues, Professor Chao Lu and Professor Chen Yanyu, also with our staff, Dr. Kamping Zhong, Xian Zhou, and Jie Hao Huo. Some of them are also affiliated with University of Science and Technology, Beijing. So the background of the paper is the following. This is actually our invited paper in JLT this year. So please refer to the paper for all the details. So we will focus on the digital signal processing (DSP) part of this very big and important field of short-reach optical communications. And by no means we think that DSP is the only important aspect of this very important area of short-reach optical communications. And so the reference we have, it's up to last year, and I'm sure we will have missed out some relevant papers, but hopefully we did not miss out those very important ones. All right, so we'll first start to talk about modulation formats for short reach systems. We'll talk about why this area becomes a new area of its own. So if you are in optical communications for a while, you would know that we have been talking a lot about DSP and modulation formats for long haul coherent communications. But then the short reach systems, it just turns out that it actually has new constraints, that it evolves as a new area of its own. We'll then talk about some of the DSP specific to short reach systems. Okay. More interestingly, there has been a lot of work in how we can do polarization multiplex systems specifically for short reach scenarios. We'll also talk a little bit about some of the advances in the different various transceiver components, because that actually has an impact on the relevant DSPs that we will develop. Okay, when we talk about short reach optical communications, in these recent years, the application is mostly for data centers. So essentially, the collection of servers for big players like Google, Facebook, and these sort of companies. Because internet traffic is quite highly concentrated in these few companies, these few years. And so basically everything that you do on a daily basis, most of the communication activities actually goes through these sort of data centers. Same for cloud computing and cloud storage. So basically it's the important backbone of our global telecom network already. So it's a fastest growing sector, both in commercially and also in terms of research activity. And that's why a lot of people are very interested in trying to come up with low-cost upgrades for such high-volume markets. Now, of course, internet traffic, of course, goes up with time, but I guess more importantly and more interestingly, what we are seeing is that if you look into the distribution of internet traffic, you realize that in these few years, most of the internet traffic is actually within or between data centers. And in fact, the part of traffic that you experience, the thing that goes to the end customers, actually constitute a very small portion of the global internet traffic. And so we were talking about, we're trying to develop a lot of 400G, 100G, or even 1 terabit per second transmissions specifically for data center short reach optical links. So when we talk about short reach optical links, we actually, a lot of people actually categorize different types of communication systems under the umbrella of optical short reach. So it can include chip-to-chip optical interconnects. So this is an interesting area. But our discussion, our paper, actually does not focus on this particular area. So we refer interested readers to go to the reference 1 of our paper for a good review of that topic. Now, short reach can also refer to the connections between server to servers. So you can imagine you have a lot of servers put in a rack, or you can imagine connections between one server in one rack to another server in another rack. So these sort of connections, you'll be talking about tens of meters, 300 meters, or 1 kilometer, and these sort of length. Okay, so typically right now we'll be using stuff such as VCSELs, multimode fibers. So another category of short reach systems is the inter-data center optical interconnects. So you can imagine you have multiple data centers that they are somehow connected to each other, and so that those links, depending on the distance between servers, okay, a lot of them are within 10 kilometers, 2 kilometers, or 20 kilometers, these sort of range. Okay, so for these sort of systems, we are typically use DML, EML, and also single mode fibers. Okay, so we'll talk more in detail about these sort of stuff later. And another area of short reach is what we call extended range inter-data centers. So these are cases when the two data centers are more than maybe 20 kilometers apart. So in that case, the technical challenge actually results in an area of its own. So there are specific solutions proposed for these particular sort of scenarios, and we will go through these things in more detail later on. Okay, so now there has been a lot of advances in long-haul coherent communications over the past 10 years. So if you are in this field for a while, you will know that actually a lot of these current research in short reach are primarily driven by the advances or the achievements in long-haul coherent communications. So the first question it may came to your mind is what are the difference between the long-haul systems and the short-reach systems that people are dealing with these few years? Okay, the first one is cost, obviously, because because of a lot of reasons. One of them is because it's such a high volume market, okay? And then you cannot afford to have very expensive transceivers. Now, of course, that's obviously true for all type of receivers as well. But then for short reach, the cost constraint is a lot bigger than long haul transceivers. So that translates into the following. For example, you wouldn't be able to use ideal transceiver components that you use in long-haul systems, okay? And a lot of times that actually means you cannot have a local oscillator, meaning you need to have direct detection. Form factor, size of the transceivers. Now, of course, that's also a feature to optimize for long-haul system as well. But then for short reach, it actually translates into the size of the rack of servers and the port density and things like that. That actually is very sensitive, a big parameter for short reach data center design, because if you take a bigger picture point of view, the size of the overall data centers actually does depend a lot on the port density and rack size, and so we actually need a lot of air conditioning for these sort of data centers. So then the size of your components translate into the size of your data centers, which translates into the energy usage for air conditioning and these sort of maintenance for data centers, and the overall energy usage actually can be quite huge. So there actually is some studies that says that the telecom and the energy usage for telecom activities worldwide has already reached about 3 to 5% of the total global electricity usage. So that's actually not a trivial part of our total energy usage as a whole. So this is actually quite an important factor, especially for short reach. Latency. So basically what that means is the propagation distance between the transmitter and receiver in short reach systems is quite small, because we are talking about short reach, right? So maybe 10 kilometers or less than that. Okay, so in that case, a lot of the forward error correction, the FEC codes that we use for long haul systems, actually when you put it in short reach, it actually becomes a problem because the FEC have some latency. So if the time it takes for the signal to transmit from the transmitter to receiver is so much smaller than the time it takes to process the signals at the receiver, then it actually doesn't make sense. And also a lot of data might actually need to go through multiple sets of transceivers before it goes out from a data center. So in that case, if you directly borrow some of the powerful soft decision FEC from long haul, you put it in short reach, the latency that you'll be experiencing will not be quite acceptable. So in that sense, for short reach systems, I think the consensus is that you will only allow a hard decision FEC or some other very interesting and innovative new ideas on low latency codes, such as staircase codes and these sort of new ideas that has been proposed in the recent few years. Okay, so now again, very rough one slide summary of the difference between long haul and short reach. It's long haul, you get to use all the best equipment, best transceiver components that you can use, and your DSP it's relatively unlimited in terms of complexity. For short reach, you are bound to use more components that might not be as ideal as you would hope for, and then in that case, how do you come up with corresponding DSP to maximize overall transceiver performance? So that's actually the main topic of this area of research, and this is what we will talk about. This is what we will talk about in this presentation. Okay, so let's just get into a little bit more technical details. Let's just start with the basic channel model, and then we'll go on and talk about how in short reach systems the channel model might actually change. Now, so this is the standard polarization multiplexed optical transmission systems. So the received signal in the X and Y polarization, okay, is the inverse Fourier transform of the transmitter spectrum, okay, and then it goes through the PMD effects and also chromatic dispersion. Now, we will not talk about fiber nonlinearity, because in the length scale of short reach systems, there is not much fiber nonlinearity. There are some works that shows if you have very high transmitter power, there are still some fiber nonlinearity, but so we will, for simplicity, we will not go into that detail in this presentation. So again, actually, because of the length scale of short reach, there's actually also not much PMD, polarization mode dispersion. So in fact, when we talk about polarization effects for short reach systems, most of the time we are only talking about polarization rotations, between the transmitted signal and some components in between, and then the received signal polarization. So this is primarily what we will focus on. So obviously, so the received signal after direct detection. So again, we particularly focus on direct detection because for cost concerns, most of the short reach proposals are based on direct detection. So basically, the receive photocurrents, okay, in principle, in both polarization, okay, it's the receives electric field, okay, and then plus whatever electrical noise that is generated from the receiver structure. Okay, so of course now if your optical link has additional amplifier noise, if you put optical amplifier, then of course you will have additional noise before photo detection. Okay. All right. So now this is a table discussing roughly how we categorize different types of short reach systems and some of the features and limiting factors. Okay. So for server to server, for the shortest type of a short reach, for those of systems that use multimode fibers, the limiting features, it's the standard traditional intermodal dispersion. Okay. So there are also some limitations for the VCSELs, the transmitter as well. Okay, and for inter-data centers, so for the ones less than maybe 20 kilometers, in fact, the features is that the receiver sensitivity might actually be a limiting feature. So that's because for those systems, it is actually not quite preferred to have optical amplifiers because of cost concerns and form factor and these sort of considerations. So in that case, your receiver sensitivity, meaning your receive optical power, might actually be the limiting factor. And also dispersion, chromatic dispersion, can be a limiting factor. Now that's because for these sort of distance, 10 kilometers and 20 kilometers, sorry, 10 kilometers, 20 kilometers, if your baud rate is high enough, you will still undergo the effect of CD. So even though the effect of CD is linear, but we are talking mostly about direct detection systems, and so the effect of CD will, after direct detection, is not a simple impairment that can be easily mitigated by DSP. Okay? And also, if people have a choice, you will still want to minimize the amount of signal processing. Right, so in that case, that's why dispersion CD can be an issue for these systems. We'll just make one remark that for these type of short reach, there are a lot of proposals. One of them including O-band transmissions as alternative, because for O-band basically there's no CD, so you can potentially bypass this problem. So for extended reach, for longer inter-data centers, or even approaching metro and access networks, the limiting factors are CD. So that's because for those length scale, basically there's no way not to use optical amplifiers. So then the receiver sensitivity is not really a concern, but then the effect of CD is still something that is not easy to take out. Okay, our remark here is that it really depends on your view, but it seems that there's a chance that for these sort of longer short reach transmissions, there may be a fair chance that actually coherent transceivers will eventually replace or get into this area, and in that case, it should be expected that we would follow most of the know-hows that we have developed for coherent transceivers in the near future. All right, so now this is an attempt to try to sum up the technical challenges in high-speed short-reach systems. So essentially, we felt that essentially there are only two major impairment or major roadblocks for short reach systems. One is the bandwidth of the transceiver components, and then dispersion, and of course also at the receiver you have bandwidth limits, and also some nonlinear effects. Now when we say nonlinear effects here, we don't mean the fiber nonlinearity, we mean the nonlinearity from the transceiver components like modulators and then the chirp and things like that. Okay, and also we'll talk in detail how if you are limited by direct detection, doing polarization multiplexing is actually quite challenging, and so there has been a lot of work in trying to realize polarization diffusion multiplex systems with direct detection. Okay, the first type of signals that we will talk about, it's pulse amplitude modulation, PAM signals, because obviously this is the simplest form of amplitude modulated information transmission. So let's just look at the one transmission in one polarization. So we all know that the simplest way to encode information is to put signals in the amplitude. So we use to encoding two levels of information we call OOK, and then we can encode 4 levels, 8 levels, 16 levels, so on and so forth. So we call this PAM4, PAM8, and PAM16. So in terms of expressing the signals, here is how one can express the signals mathematically. Okay, so the transmitted signal are the information, okay, and then the pulse shapes, okay, and then the TS here is of course the symbol period. And obviously, if you encode more information, you would need higher signal to noise ratio to achieve a certain bit error ratio. So in these days, the most popular form of PAM signals is PAM4. And here is another way to encode information on the amplitude. So this is what we call carrierless amplitude and phase modulation, CAP. Okay, so essentially, basically, the idea is to transform complex signals into real signals for IMDD systems. Right? So conceptually, it's quite similar to a heterodyne detection. So what you have here is that you have your information A and B, okay, and then it goes through a shaping filter G. Okay, so typically, square root raised cosine function. Okay, and then you multiply itself by cosine and sine, so that actually these two signals form the Hilbert pair transform. Okay, so then you put it in the channel, and then when you detect it, you will be able to recover both the A and B. So it's conceptually similar to heterodyne detection. So this is an implementation of a block diagram of the CAP system, and if you look at the impulse response, you can see that they are supposedly Hilbert transform pairs. Okay, so if you look at frequency response, basically again it will look like heterodyne signal transmission. Our third way to modulate information in the amplitude of the optical carrier, it's what we call discrete multi-tone. So essentially that is just OFDM for direct detected systems. Okay, so what you have here is that the transmitted signal will be a sum of different subcarriers, okay, of information encoded in different subcarriers. Okay, now to make sure that the overall signal here is positive, it's real and positive. So what has been done is first of all you make sure that the signal is conjugate symmetric. So meaning the negative subcarriers are actually the inverse or this complex conjugate of the corresponding positive subcarriers. Okay, and also the zero subcarrier or DC value a lot of times is raised to a certain point where the overall signal is always positive, so that you can do direct detection. All right, so of course, as a particular example of OFDM, one will need to have first serial to parallel conversion of data, okay, and then also insert a cyclic prefix, just like typical OFDM systems. And in the receiver, of course, the reverse process also applies. All right, and so one of the obvious advantages of DMT, it's the ability to do what we call bit loading. So basically, that's the idea of encoding different modulation format on different subcarriers based on the quality of that subcarrier. Okay, and of course, when you do that, the first step is to estimate the channel. So there are also a lot of works on trying to perform channel estimation efficiently. Okay, so this is the transceiver setup for these three signaling formats that we have just talked about: PAM, CAP, and also DMT. Okay, so so essentially, it is quite similar to what you would expect in traditional long haul coherent, not coherent, so traditional long haul systems. Okay, and also a lot of the signal, the processing blocks are quite similar to what you have in standard telecom systems. Okay, all right. So there are other more complex modulation formats. For example, multi-cap. So basically, you have multi-carrier transmission, and each subcarrier is a cap signal. You can also have this what we call orthogonal PAM DMT, in which case you have a certain bandwidth of certain frequency range for you to encode information. So part of it you use PAM, part of it you use DMT. So there are a lot of these sort of proposals that are around in the literature. So I guess one of the more important points here is to sort of compare which type of modulation formats are particularly suited for our short reach optical systems. Okay, so here it's a table of recent demonstrations using these three formats. So I think the first demonstration of PAM4 at 100 gig, I think it is given by a group from DTU, and then we ourselves have performed some of these PAM4 experiments as well, in like 140 gig, and then also a WDM transmission. I think it's the group from NTT that actually demonstrate one of the highest speed 214 gigabit per second transmissions, PAM4. I think in OFC 2016. So that's for PAM4, and for cap signals, I think we also publish some works on cap 16 together with the group from Fudan University of China. For DMT transmissions, I think Fujitsu have done a lot of work on demonstrating the potentials of DMT, and I think most recently there has been demonstrations of above 500 gigabit per second by I think a group in ZTE and also Fudan University. So now here are three parameters that we have compared, and basically the three parameters are received optical power, the transmitted bandwidth, and the rain noise. Okay, so in terms of received power, I think all three formats behave similarly. In terms of transmitted bandwidth, actually DMT has the best performance. That is primarily because is after all OFDM signals, and then if the more subcarrier you have, the sharper the overall spectrum it is, sharper roll off. And perhaps because of that, actually the ring noise tolerance, on the other hand, is the worst for DMT signals. Okay, so you can refer to the paper on the actual parameter values that we use in this comparison. And now, finally, this is a graph showing the bit error ratio versus the received optical power. I guess what we wanted to highlight is the following. All these formats have similar received sensitivity performance. Okay, however, DMT is actually computationally simpler, right? Because it is OFDM based signaling. So a lot of times when you process signals in the frequency domain, it is somewhat easier than processing signals in the time domain. Okay, but then DMT actually suffers from another issue, and that's the ADC resolution. Okay, because naturally, compared to PAM4 signals, DMT signals looks more like analog signals. So you would need higher ADC resolution and DAC resolution, obviously. Okay, and also the DMT signals, by the same reason, would require better linear amplifiers when the signals is in the electrical domain. Okay, so considering all these hardware complexity and DSP complexity, I think the field has evolved to a point where PAM4 is basically won the debate. Is considered as the better choice for practical applications, and you can see that actually a lot of the standards that is developed are based on PAM4. Okay, a lot of the products developed are based on PAM4. There are one or two companies that actually have DMT as their product, but I think that is the minority. Most of the transceivers design are actually based on PAM. Also, note that a comparison of higher order modulation formats such as PAM8 and CAP64 and these sort of signaling actually is presented in a paper in reference 10. So the interest reader can go there and take a look. So the next thing that we'll talk about are the DSP aspects of short reach systems. And so essentially, most of the DSPs in short reach systems are implemented in the transmitter either as a pre-emphasis or some sort of equalizations at the receivers. So obviously, in addition to equalizing a lot of linear impairments that we know from linear systems, some of the more interesting impairments that we need to compensate are things such as bandwidth limitations and also various sorts of nonlinearities arising from direct detections, modulators, and other device imperfections. So let's just talk about two of the very standard basic equalization methods. So the first one is, of course, the feed-forward equalizer. So essentially, what we have here is that basically we have a discrete time filter W, okay, and then what it's trying to do is trying to have the input signal, which typically is the received signal, okay, at the receiver, okay, passive for a filter. So hopefully the output Z is a quantity that is as close to the original bit sequence as possible. So essentially, hopefully the filter has equalized the channel. Okay, and another standard technique it's what we call the decision feedback equalizer. So in this case, what happens is that instead of equalizing the received signal, we actually first make decisions and then try to recreate the amount of impairment, okay, so that we are able to cancel out, in a sense, cancel out the interference caused by neighboring symbols. Okay, and so these are two very standard DSP techniques in general communication settings, and we'll see how all these techniques are applied in short reach systems. Alright, now it should be noted that feed-forward equalizers are relatively simple and does not suffer from any feedback delays, but it is not very effective when your transfer function has a 0. Okay, so in that case, the FFE cannot really compensate for a spectral null. Decision feedback equalizer, DFE, on the other hand, you can successfully equalize these spectral nulls, but it might become unstable because it might suffer from decision error propagation. So in our case for fiber optics, since one of the major transmission impairment is chromatic dispersion, so it actually induces intersymbol interference that contains both interference on future symbols and past symbols. So therefore, the best choice of equalization is always a combination of the feed-forward and feedback structures. In addition, one can use concepts such as the Tomlinson-Hiroshima precoding. So it's the transmitter side DFE. It can be used in our scenario, and it does not suffer from error propagation. So another direction of digital signal processing that one can think of is what we call a Volterra series nonlinear equalizer. So what we have discussed just now is mainly for compensation of linear impairments. So as we know, in short-reach communications, there are various sorts of nonlinearity. So not the traditional fiber nonlinearity per se. It's also a lot of nonlinearity coming from the transmitter components, and also, for example, direct detection itself is a nonlinear operation. So in the simplest form, the Volterra nonlinear equalizer contains two components. So you have the linear part, okay, with the weights, with the weights here, okay, and also there's a nonlinear part. Okay, so this is the simplest form of the Volterra nonlinear equalizer. It contains a term, okay, that actually has the square of the input signal. Okay, so this is a second order nonlinearity. So in principle, one can continue to have additional terms that incorporates the third order, fourth order nonlinearities in the signal processing block. Okay, so now for all these equalizers, we would need to find the right weights, the W, okay, so that we can obtain a good signal output for decision. So how do we typically obtain these values of the what we call the tap weights? So typically we would use adaptive signal processing. So meaning we don't assume that we know the channel transfer function exactly, and we don't know the nonlinear interference or nonlinearity part of the transmitters in advance. So we would need to guess or find the best sort of filter weights sort of on the fly. Okay, so the way to do it is typically to use adaptive signal processing techniques such as least mean squares. Okay, so essentially the idea is pretty simple. What you want to do is you would want to define a function, a cost function j, as a function of the weights. Okay, so that it's actually the expected mean square error between the filter output and the original bit sequence. Okay, so we would want to find the filter tap weights W that minimize this cost function. Okay, so typically in all areas of numerical optimizations, one of the major techniques is to use gradient descent. Okay, so you start off with some initial estimation, and then you iteratively update the estimate of the optimal filter weights. Right? So essentially, it is just obtained through gradient descent. So each time, for each iteration, you go into the direction of the gradient of the cost function. Okay, so if you put in all the algebra, and essentially this is essentially the what we call update equation. Right? If you start at the n+1 iteration, if you start your iteration at the k0 time slot. Okay. All right. So also, in this case, we would need to know the bit sequence in advance. So that is typically done through pilot symbols. Okay. After a while, when it has achieved a certain convergence, okay, typically we will switch the operation into what we call decision-directed LMS. Okay, so you replace the pilot symbols with your decided symbols. Okay, so note that this can only work when your filter tap weights is pretty good already. Okay, we're pretty close to the optimal configuration already. So recently, so we proposed a new hybrid structure called the decision-directed faster than Nyquist. Okay, so it consists of 3 components. Okay? So the first component is a regular FFE. Okay, and then what we do afterwards is that we actually pass the filter output of the FFE through what we call a post filter. Okay, and then afterwards we put it through a maximum likelihood sequence estimation. Okay, so the rationale is the following. So we did mention that the feed-forward equalizer is not good at equalizing spectral nulls. Okay, so in more detail, it is because when you try to invert channel with very low magnitude at certain frequency, typically at high frequencies, when you equalize this effect, you actually enhance the noise. Okay, so so it is because of this that when you, for example, when you have a channel that it's very band limited, okay, and then you send a high bandwidth signal through this channel, then when you equalize the channel, you essentially you amplify the high frequency components, but at the same time you also amplify the noise at the high frequency components. Okay, so there's this thing called noise enhancement. So now, however, when it comes to the using adaptive signal processing, the LMS doesn't really care about the noise enhancement. It just tries to find filter weights that matches the output to the original bit sequence as much as possible. Okay, so therefore, to try to mitigate the amount of noise enhanced based on the FFE architecture, what we have done is that we essentially have this post filter that actually, have essentially built a low pass sort of effect on the equalized symbol. So it's like doing the opposite. Okay, so in that case, this post filter does suppress some of the enhanced noise. Okay, but at the same time, it also suppresses some of the signal component at high frequency. Then what do we do to that induced intersymbol interference? We use the MOSC, okay, to take care of the residual intersymbol interference caused by this post filter. Okay, so this is trying to achieve a trade-off between noise enhancement and also equalizing the channel. Okay, so we have done quite a bit of experiments and numerically figure out what is a good combination of of this FFV and post filter and MOSC, memory length, and so on and so forth. And so we are able to demonstrate 140 gig PAM4 transmissions in the O band over 20 kilometers with an O band for our short reach systems. Okay. Now, let's look at the effect of chromatic dispersion, CD, with direct detection. So let's assume we have transmitted signal S, okay, and then A is the carrier. Then in that case, the electric field at the transmitter would be the square root of A plus S, okay, because we are assuming that we are directly modulating the laser source. And so in this case, the channel response that models CD, it's basically given by this, okay? And so the interesting thing is, if you have direct detection at the receiver, okay, and what happens when it is combined with CD is the following. So the received signal, the received signal is the received electric field magnitude square, okay, given by this here, where of course this is the convolution. And when A is large, then you can approximate this as the following, okay. So when ST is real, okay, then we can approximate the channel response as the average of H of T and also its complex conjugate. Okay, so the equivalent transfer function has a response that has a cosine component. Okay, so the functional form is cosine of the frequency square. Okay, so this actually becomes a major issue, because what that means is that there will be channel fading when we have CD and direct detection. So this is something that coherent communications do not suffer from, okay, because cosine will go to 0, okay. And more importantly, so this fading actually depends on the transmission distance. So the larger the distance, L here, then you will have stronger fading. So that's shown in the graph on the left. Okay, so this becomes a major problem. So if you want to transmit for longer distance, you have more fading, meaning your signal bandwidth will be less, and then meaning your transmission speed will be less. Okay, so this is one of the unique features of direct detection systems. So how do we get around with this problem? Now, there are a few approaches. Okay, first of all, you can do CD pre-compensation. Okay, but typically we would need large form factor and expensive IQ modulators. So these sort of ideas are not new. We have seen these sort of approaches in coherent communications a decade ago. But then for short-reach communications, I guess we are even more constrained in terms of the device form factors and power consumptions. Dual drive MCM may be a better choice in this scenario. But in any case, we need to know the amount of link dispersion in advance, so that can be a disadvantage. Another approach is to use O-band transmissions. So basically, if you have lasers at 1310, then there is no dispersion, so this problem automatically disappears. Now, however, we don't really have O-band amplifiers, and one of the most recent standards for O-band transmissions will support 4 WDM channels only. So these two things together severely limit how much these idea can scale. Or you can use non-zero dispersion shifted fiber. Okay, so in principle, there's actually nothing nothing in physics that prevents this approach from being useful. Okay, it's only It's only just that the production volume of NCDSF is rather low compared to standard single mode fiber. So that doesn't seem to be a very attractive option at this moment. And finally, we can actually use single sideband signaling to address this problem. Now, how come with single sideband signals are able to address this dispersion-induced fading problem? Now, in this case, what happens is the following. Now, if you have single sideband signals, that means the baseband signal S in this case is actually no longer real. So what happens is that if S is no longer real, then actually some of the derivations before the equivalent channel response, actually that becomes not true, and hence all the subsequent effective channel model of channel transfer function of a cosine frequency square, that actually is no longer valid. So what happens is that if you transmit a single sideband signal, so this is the signal spectrum comparing single sideband and double sideband, the received signal spectrum actually does not suffer from any CD-induced fading. Okay, so as shown in the graph on the right. Okay, so the graph on the right is showing essentially the SNR, meaning the amount of power, received signal power, as a function of subcarrier numbers, also meaning frequencies. So you can see that for double sideband signals, there's a significant amount of fading. Okay, but then for single sideband, there's essentially no fading. All right, now let's look at a single sideband signal in a bit more detail. So at the transmitter, you will have the transmitter signal to have a DC component and the single sideband signal. It is carried to a certain area, certain range in frequency. And so at the receiver, so basically this transmitted signal has undergone the channel, which primarily have CDs among other things. And so if you expand on this, this is what you will get. So you have three terms, and then the term in the middle is the signal term that you want, and the term here on the right is what we call the single sideband interference. Now, so there are two situations for these SSB systems depending on the carrier frequency FB. Okay, and so in one case, if your carrier frequency is such that the single sideband signal and the SSB interference do not occupy the same frequency range. Okay, so this is what we will call a guard band SSB signal. Okay, so the advantage of that is obviously, if you look at the figure, there is no spectral overlap, and so you can easily filter out the single sideband signal without distortions and interference. And the other case is the case when there is no guard band, okay, meaning the single sideband signals are just right alongside the carrier signal. So in this case, the advantage is, of course, it saves a lot of spectrum, so it's good for spectral efficiency purpose, but then the SSB interference does overlap with the SSB signal. So we will need to find ways to eliminate the SSB interference. Now, so let's look at this question of mitigating the SSB interference. So of course, actually, the one simple way to eliminate the interference is to have a very large DC power. Okay, because this term, the signal term here, actually depends on the amplitude of the DC signal. Okay. Now besides that, there are still a lot of other ways to try to eliminate the SSB interference. In particular, we'll show how we can actually make use of the signal in the middle, the signal that we wanted, and then we can use that to reconstruct or recreate the SSBI, and then in that case we can actually cancel out the SSB interference. Okay, and so there will be a few ways to do this. Now the first way, it's a feedback mechanism. It's a feedback iteration method. So for the purpose of discussion, let's just assume it is an OFDM signal. Okay, so now if you start from the receive signal, if you do the FFT, then what you will get is the spectral component at frequency index k. Okay, consists of the following: is the original signal, and then the channel transfer function, and then the noise I. Okay, and then the A again is the DC carrier, DC signal. So then what we can do is we first cancel out divide the C by A and H. Okay, make a decision here, okay, about the transmitted bit B. Okay, and so let's say you have some rather acceptable detected signal. Okay, so you can in principle recreate the transmitted signal, single sideband signal. So in this case, then what you can do is the following. So you can use the decided signals to recreate the single sideband signals. Okay, and then in this case, then you will use the recreated signal here, and you can beat with itself. And so in that case, that is by definition the estimated SSB interference. Okay, and then by here, then you can use that to cancel out the original SSBI in the original receive signal. Okay, so this is one way to use the receive single sideband signal to recreate the SSBI, and then cancel that out from the original receive signal. Okay, so in this case, of course, we would need a large carrier to power ratio. The constant A needs to be large enough to ensure correct iteration convergence, okay, and avoid error propagation. So this process needs to be iterated a few times, typically more than 5 times required to obtain good SSBI cancellation performance. Okay, so this is one feedback method to eliminate SSBI. Now there are other methods. For example, instead of feedback method, there is also a feed forward method. So the idea goes like this. So let's say at the receiver, at the receive signal, you have the SSB signal, the blue one that you wanted, and also the SSBI, the triangle. Okay, so what you can do is you can extract the one of the sidebands. Okay, so here we have this what we call the sideband filter. Okay, then you got one of the sidebands. Okay, so in that case, the blue, it's the original SSB signal, and then you do a direct detection, and then you divide it by the carrier power A square. Okay, so in that case, you actually recreate the SSBI, the triangle. Okay, so in that case, you can use that to cancel out the original receive signal. Okay, and then you do a sideband filter again, and so in principle, this is how you can eliminate the original SSBI. Okay, so so at the end, what you get here, okay, will be the original signal minus two other terms, okay, but then these two other terms are much smaller than the original SSBI, as long as the carrier amplitude is large. Okay, now this concept of feed-forward SSBI cancellation can be taken even further. So you can actually have a two-stage feed-forward method to eliminate the SSBI. So basically, this is a continuation of what we talked about just now. So what we talked about just now is that we have renewed estimation of the signal as given by this expression here. Okay, so there's these two extra terms. Technically, the two extra terms are the SSBI and signal beating term, and what we call second order SSBI. Right? So both of which are much less than the original SSBI already, but still we can actually extend our concept and also recreate this term SSBI signal beating term to further eliminate this term. Okay, and then this is the structure that attempts to recreate the SSBI signal beating term from the output of the first stage feed-forward method. Okay, so in this case, then again we will be able to further eliminate this term. Okay, it will again create other terms which are even smaller. Okay, so this is going to be a two-stage feed-forward method to try to eliminate the single sideband interference due to the fact that the single sideband signal does have spectral overlap with the single sideband interference. Okay, besides single sideband interference cancellation, another approach that is related to single sideband signals, it's what we call KK receivers. So it is first proposed by the Marcuse group in 2016. So essentially, the idea is that the signal itself needs to be single sideband, okay, and so the information signal, as it can be precompensated for transmission impairments. So the overall signal with the carrier should look like this. And so what happens is that if you have enough CSPR, the carrier to signal rate ratio, to achieve this what we call minimum phase condition. So what that means is that the signal trajectory doesn't really encircle the origin as shown on the graph at the right. Okay, so if that is true, then one can show that the phase and amplitude of the overall signal are uniquely related. In particular, at the receiver, once you receive the direct detection signal, okay, then one can actually recover the amplitude and phase information of the information signal as follows. So the phase of the information signal, okay, actually can be obtained by calculating the Hilbert transform of the log of the direct detected current. Okay, so in this case, we will be able to both recover the amplitude and phase of S. Okay, and so this is what we call a KK receiver. Now, since 2 years ago, we have seen quite a lot of KK experimental demonstrations. Okay, so the first one, it's from a group from UCL. It just demonstrated pretty high spectral efficiency of, I think, about 4 bits per second per hertz. Then the group from McGill and Sienna can also demonstrate using a twin SSB. So basically, have two SSB signals in two silos of the sideband. Okay, and so they can demonstrate 88 gig transmissions. Also, one can extend the concept and then demonstrate polarization diffusion multiplexed KK receiver. So this is also reported by the group from McGill. Okay, and finally, one can combine all the concepts in WDM and POMUX and KK receiver, and so this is a demonstration by Bell Labs that has demonstrated, I think, net spectral efficiency of 5.3 bits per second per hertz. So so it turns out that the KK receivers generally require lower CSPR to satisfy the minimum phase condition compared to the zero guide band, single sideband signals that we have discussed in previous session to compensate the SSPR effectively. So in a way, the KK receiver has less stringent requirement on the CSPR. And finally, one should note that because these systems naturally require you to have a strong carrier, so it turns out actually low-cost modulators such as the dual drive MCM are actually quite suitable for these sort of systems with large carrier component because it inherently has a large carrier component in its signal generation. Okay, next we will talk about POMUX systems. Now, POMUX systems is one of the most important component of current coherent systems, but it's actually not that straightforward to implement with direct detection receivers. Now, since about 2014, people have proposed this idea of a Stokes vector direct detection receivers that can make use of POMUX signals to encode more information. Now, so let's just do a little bit of recap of signals representations in Stokes space and also Jones space. So typically, in Jones space, we represent signals in two polarizations with two signals, EX and EY. Okay, and the Stokes space representation is given by these four expressions here. So essentially capturing the signal amplitude, power in both polarization, as well as capturing the phase difference between the signals in two polarizations. Now, upon transmission through the fibers, there will be polarization rotation of the signal. Okay, so in Jones space, it is captured by this matrix. Okay, and the mathematical equivalent of this matrix in Stokes space will be given by this matrix here. Okay, and so we will talk about two-dimensional, three-dimensional, and four-dimensional POMUX direct detection receivers. So here, the dimension means the degrees of freedom. Okay, so why do we have separate schemes for two-dimensional, three-dimensional, and four-dimensional signals? So that's because it's actually not that easy to leverage, to exploit all degrees of freedom for information encoding when you have direct detection receivers. Okay, so let's just talk about two-dimensional POMUX direct detection systems first. Okay, so even that we have a few ways to implement, to realize such schemes. Okay, the first scheme basically can assume that signal in one of the polarization is essentially unmodulated. So the signal in this path is unmodulated, so it can act as a carrier. The signal in this path, it can undergo complex modulation, so with I and Q. Okay, and the receiver structure consists of a few PDs, okay, and also 90-degree hybrid and then balanced photodiodes, so that one can recover both the signal power in both polarizations as well as the phase difference between polarizations. So note that here there should be some 90 degrees polarization rotator in one of the input to the optical hybrid, so that the signals in both polarizations can beat with each other. Okay, so this is the Stokes vector at the transmitter, and so as we have discussed previously, we would need to estimate the rotation matrix so that we can recover the transmitted Stokes vector from the received Stokes vector. Now the way we can do it is by, one can actually use regular palette symbols. Okay, so in this case, one can send just 3 palette symbols that exploits the principal axis of the Stokes space. Okay, so in that case, you can quickly estimate the numerical values of the rotation matrix, and then use that to recover the transmitted Stokes vector. So this is proposed by the group in University of Melbourne, and I think the best achievement that has presented actually demonstrate 336 gig transmissions over 600 kilometers of single mode fiber using 16 QAM signals. Now this is another scheme to implement two-dimensional Stokes vector, POMAX Stokes vector direct detection systems. Okay, so in this case, the signals from both polarization, okay, will be intensity modulated. Okay, all right. So there's no complex IQ modulation, but then both signals in both polarizations are intensity modulated. Okay, and so the receiver structure is the same as the previous case. And then once you obtain the received Stokes vector, what you can do is that you can pass it through some sort of linear filters, okay, captured here. All right, so the linear filters here essentially tries to mitigate or equalize some of the transmitted imperfections and also some overall intersymbol interference cancellation due to various imperfections along the transmission link. Okay, so in particular, the transmitted Stokes vector, especially ST1, okay, it will be the output of 3x1 filter, where the SR1, SR2, and SR3 will be the input. Okay, so that will be more complicated than the case to recover ST0. Okay, so once you have obtained an estimate of the first 2 entries of the transmitted Stokes vector, then the original signal amplitude from both polarizations can be estimated easily. Okay, and so this is a scheme proposed by the group in McGill. And so with that proposal, I think one of the best achievement is about 224 gigs POMAX PAM4 over 10 kilometers. Now we also propose another realization of 2D POMAX direct detection receivers. Okay, so the transmitter is the same as the previous case with the McGill University, basically having intensity modulation in both polarizations. At the receiver, however, we do not use any optical hybrids. Instead, we actually use 4 simple photodiodes with 45 degree polarization rotator in one of the arms. Okay, and so in this case, we will get 4 amplitude signals. Okay, and so when one can work out the mathematics, and then this is how the transmitted signals are related to the received signals that we got from our setup. Okay, so now here in this case, the relative phase between the transmitted signals in both polarizations actually is not relevant to us. Okay, and then we can remove it. Okay, that's because our information is encoded in the intensity of the transmitted signals in both polarizations. So then the DSP starts with trying to eliminate these terms. Okay, and the first step is to first estimate the one of the rotation angle theta. Okay, so you can do the algebra and then show that this can be estimated by this expression. Okay, and then once you get the estimate of the angle theta, then the next thing is to try to remove the term, the phase splitting term. Okay, so one can actually just essentially just do some simple linear algebraic operations on the rows of the equations, the set of equations here. Okay, all right, and then so finally one can actually show that we can eventually calculate the transmitted signal intensities in both polarizations. Okay, now here is comparison between all these schemes that we propose for 2-dimensional COMAX direct detection systems at 100 gig. So the detailed parameters of the simulation comparison can be found in the paper. So the graph on the left is is to show the bit error ratio as a function of the receiver sensitivity. Okay, and so you can see here that the case with the hybrid and intensity modulation on both polarizations actually has the worst receiver sensitivity. Okay, now one of the things that we want to highlight here is that if you actually count the additional loss by the hybrid, the performance of the schemes that requires a hybrid will be worse. So you can see if you take the 7% efficiency threshold as a benchmark, so you can see that with practical hybrids, the receiver sensitivity actually is pretty good for the case with only photodiodes and no hybrids. Okay, and so in terms of the receiver sensitivity, so the trend is that it is desirable if you can actually not even use the 90-degree hybrid. Now the graph on the right shows the tolerance of the proposed schemes to chromatic dispersion. So in this case, it's obvious that the first scheme with complex modulation in one polarization and unmodulated carrier in the other polarization, that will be robust to CD because you essentially coherently receive the complex signal, in which case you can do a lot of signal compensation. Okay, so therefore it is clear that the complex modulating scheme will be very good in terms of longer distance transmission. Okay. Okay, next we will talk about three-dimensional POMAX direct detection systems. So in this case, the information is encoded in all 3 degrees of freedom of Stokes space. Now the first scheme that achieves three-dimensional POMAX direct detection system is basically just adding one phase modulator in one of the signal polarization. So in this case, what we are detecting is the phase difference between signals in the 2 polarizations. So we call it the interpolarization phase. Okay, so if you look at the Stokes space representation of the signal, you can see that the phase between the 2 polarizations are inherently encoded in the S2 and S3 parameters. So in this case, the receiver is just one of the Stokes space direct detection receiver that we have talked about in previous cases. And in terms of the receiver DSP, so there are a few ways you can do it. You can have a 2-stage setup. So basically, that will be a 4x4 MIMO, okay, that tries to estimate and equalize the polarization rotation, okay, and then followed by a single in, single out filters. And so this is to again mitigate the residual transmitter intersymbol interference of the 2 intensity and phase waveforms. Now there you can also do implement a 3-stage receiver structure, DSP structure. Okay, so in this case there is a separate single in, single out filters before the MIMO. Okay, so in that case, this is of course to mitigate the intersymbol interference, and also this can help reduce the length of each taps of the subsequent 4x4 MIMO filter bank. So this is another proposal by the group from McGill University. And so with this 3-dimensional scheme, okay, so one can significantly improve the overall bit rate. So a total of 460 gig transmissions was demonstrated over 500 meters. Right, another scheme to realize a 3-dimensional POMAX direct detection system is actually, interestingly, to have a carrier in one of the polarizations, and then the signals from both polarizations undergo IQ complex modulations. Okay, so you might think that this sounds like full coherent sort of signals, but actually it is not. So what happens is that what you will generate signal that looks like this, okay, and then at the receiver, what we'll do is the following. First, of course, estimate the polarization rotation matrix, and then equalize it, cancel out the phase rotation, and then so afterwards, then you will get the an estimate of the transmitted Stokes vector. And so the next step is to recover the signal, the X polarization. So essentially, the at the signal at X polarization, the signal power is essentially just the sum of the S0 and S1 component. So you can see that it contains a few terms, okay? And then this term is the term that we desired. Now notice that we are only able in this setup to recover the real part of the EX, of the signal in X polarization. Okay, so in this case, we can recover the imaginary part by something called a signal phase switching. So essentially, it is like in the second signal block in the next symbol interval, you will send the original signal in the X polarization, but then multiply by J, right? So that in the next symbol time slot, you will receive the imaginary part of the bidding between the carrier and EX, right? So in this case, then over two symbols, you can get the real part and the imaginary part of this particular signal. So in this case, then afterwards, we can use methods such as direct reconstruction to remove the effect of interference, and then also calculate, estimate the fully the signal EX. Okay, so because of that, you essentially reduce the spectral efficiency of the signal in the X polarization. So therefore, even though we are talking about complex modulations, the I and Q of the signal in the X polarization, essentially you are only using 1 degree of freedom for the signal in X. Okay, then for the signal in Y, this is rather straightforward. Once you get the signal in X, okay, and then you look at the recovered Stokes parameter S2 and S3, then you can realize that once you get X, and then you can simply get an estimate of the signal in the Y polarization by dividing S2 plus J S3 by EX plus A. Okay, so in total, you effectively have 3 degrees of freedom in this case, and so they're able to achieve about 200 gig transmission using 16 QAM OFDM format over 160 kilometers of single mode fibers. So this is by a group in Future Way. And lastly, there are actually attempts to try to achieve 4-dimensional POMAX direct detection systems. Okay, so the idea is pretty interesting. So it is built on top of the 3-dimensional POMAX signals that we just mentioned just now. Okay, so in this case, now not only you have 2 degrees of freedom in the intensity modulation of the signal in 2 polarizations, okay, and then this is the phase difference between signals in different polarizations, so that's 3 degrees of freedom. Now the 4th degree of freedom is on what we call the polarization, in the interdifferential polarization phase. Okay, so what that means is it is essentially the phase difference between the signal in the X polarization and the last symbol in the signal of the Y polarization. Okay, so that turns out to be an additional degree of freedom to encode information. So you can think of this as the following. So essentially what we have right now, it's that we actually have 2 independent signals in 2 independent polarizations. Each of them actually has a DPSK signals, and then you also know the phase difference between the signal polarizations. So in this case, essentially, you would equivalently have all the degrees of freedom of full POMAX coherent systems, right? Because you have 2 separate DPSK systems, and then you also know the phase difference between the polarization. Okay, so this is 4-dimensional, and so the DSP for the four-dimensional system will actually be quite a bit more complicated. Okay, so the first four parameters, W1 to W4, those are something that we have discussed in previous cases. Okay, now the interesting thing is the so-called inter differential polarization signals, the W5 and W6 here. Okay, so turns out the way to recover it is by having an additional hybrid. Okay, now however, one of the requirements for appropriately demodulating this signal is that the polarization rotation matrix of the system needs to be fed back to the transmitter, right? So that the transmitter can pre-rotate the transmitted waveforms. Okay, you actually need that so that the W5 and W6 can be recovered correctly. Right? So this represents a little bit of some additional complexity, and there are maybe some issues regarding the feedback delay. Okay, so this is a proposal by a group from McGill University, and so they were able to achieve 320 gig transmissions using POMAC systems, and then the module format is 2 rings with 8 PSK on each ring. So it was transmitted over 20 kilometers. Okay, lastly, we just want to spend a little bit of time to talk about advances in transceiver components. Now, while these are hardware advances, the overall performance improvement actually depends on the kind of DSP you apply to it as well. So in a sense, a lot of these hardware advances are all tied together with corresponding DSP developments. Now, the first type of components that we want to talk about are VCSELs. Okay? So as we know, VCSELs are typically multimode. Okay, and so when you put it in a multimode fiber, it will create intermodal dispersion, which is not good for transmissions. So one can design and fabricate mode filters, or you can intentionally leak the signals in higher order modes so that at the receiver you get the signal you get mostly are signals in a lowest order mode. Okay, and so there are quite a bit of approaches on that front, and so we try to make use of some of these relative new devices to perform some transmission experiments. So this is spectrum showing the comparison of the overall system spectrum for multi-mode VCSELs versus single-mode VCSELs. So you can see that the single-mode VCSELs actually has wider bandwidth. Right? So we were able to demonstrate 100 gig transmissions for this particular experiment. Okay, and so here is another experiment by the group from HHI. So they were able to demonstrate about 160 gig DMT signal, and then what they do is they actually use some pre-equalization at the transmitter to compensate for some of the impairments in the intermodal dispersion and also on the multimode VCSELs. So another area is the fiber itself. Okay, so we are used to designing fibers at multimode fibers at 850 nanometers, and turns out there are new efforts to try to extend the range of wavelength that we work on. So in particular, so there's this new consensus of shortwave WDM. So basically 4 WDM channels around 850 nanometers. So in that case, one can actually design the index profile and geometry of the fiber so that the overall intermodal dispersion, or the overall expected product bandwidth distance product, is maximized. Okay, so this is some of the work done by OFS to try to develop new fibers so that the expected distance bandwidth product is relatively high across all 4 wavelengths. Okay, so so in that case they were able to demonstrate a total of I think 200 gig transmissions using PAM4, using all these all the 4 channels over 150 meters of multimode fiber. All right, another area it's of advances is on how to increase the receiver sensitivity, or how to decrease the effects caused by low receive power. Okay, so now one approach is to try to package all the pin and also the an optical amplifier before that. Okay, so this is one of the group by the 35 Labs. Okay, so they package the optical amplifier and the pin chip together with the TIA. Okay, so in that case, it alleviates some of the concerns in the receiver sensitivity. Another approach is to use APD, avalanche photodiode. Okay, so so there are new avalanche photodiodes with high bandwidth. So we managed to obtain one of these newer APDs from Silicon Photonics. So they have new APD with 3 dB bandwidth of about 25 gigahertz, and so we were able to perform transmission experiment of 112 gig PAM4 transmissions over 40 kilometers of single mode fiber without amplifiers. So this is a good record to show that even without amplifiers, you can actually support 40 kilometers of transmissions. All right, another area, and it's this thing called a double side EML. So it's actually some new ideas and designs on the transmitter components. Okay, so what it does is basically it goes like this. It has DFP in between, and then you have a EAM at the left and the right of the DFP. So essentially, it serves as 2 EMLs. Okay, so you can modulate the EAM at the left and modulate the EAM at the right, and so that becomes 2 EMLs with the same wavelength. Okay, so the graph on the right are just to show the characteristics of this double side EML. So this is from the HHI group. Okay, and so we managed to be able to take this and then do experiment of 240 gig transmissions, POMAX transmissions of NRZ signals using this DSEML. So some of the signal projects that we use are the stuff that we have mentioned before. So basically DDFDN, and also some maximum likelihood sequence estimation to try to maximize the performance of this particular component. Right. So lastly, we want to mention that again, this field of short reach optical communications is a very important field, and one of the key technologies is DSP, but there are also other technologies that are quite important to this overall development. So now, as opposed to having better and better DSP, there are also other approaches to actually try to minimize or eliminate DSP at all. So for example, the group in Stanford, Professor Khan has proposed to use DSP-free transceivers. So basically they wanted to do a lot of these DSP functions like polarization recovery, carrier recovery, using analog electronics or very basic logic blocks. Okay, so that's one interesting direction, and no one should forget that actually a lot of the real advances also are from silicon photonics, right? So it has become one of the biggest area in short reach communications, where we are now able to integrate a lot of different transceiver components like lasers, modulators, couplers, and everything into a silicon flavor. So that is also a very important development that is relevant to short reach communications. So in summary, I think what we are trying to say here is that advanced module formats and DSP can significantly improve direct detection performance for short reach systems. And obviously, DSP plays a key role in system design and optimization. So I think we have shown quite clearly that simple direct detection using PAM4 can achieve 100 gig per lambda transmissions already. So there are a lot of interesting proposals for polarized multiplex transmissions that can enable 200 gig and more, but then we'll have to see how the field will consolidate and select the right approach. And again, last but not least, a lot of the device advances in short reach are tied together with DSP capabilities, because again, we are mostly forced to use devices that are not ideal, and so in that case, the DSP actually plays a key role in whether some new device actually bring about a lot of or substantial improvement in transmission performance. So that is possible only if we also manage to find the right DSP to unleash the power of the devices. Okay, so I guess that's all, and we are pretty sure that we have not covered everything that has happened in the field regarding DSP, but I hope that we have covered most of the important developments. Okay, so thank you.